So we'll do this problem as an example of a conservation of momentum problem where objects start together and break apart. Except it's got a little bit of a twist. So if we read the problem, a two-stage rocket, that's a rocket ship that has two parts. So if you wanted to, you could even include here's the front of the rocket ship, right? So this is what they refer to as the lower stage, and this is the upper stage. And at some point, what happens is once all the fuel is used in the lower stage, it is detached via this small explosive charge that they talk about. So two-stage rocket moves in space at a constant velocity of. So what makes this different than the Shack problem is that before they split apart, they are not stationary. They are actually moving. So the original velocity of both sections, because they're connected, is 4,320 meters per second. And I like to break these into a before or initial situation, and we'll look at an after underneath. And I find when I work a momentum problem like this, or any momentum problem, I like to try to look at both situations, have a picture for each. So, moving that fast, we know the mass of each piece, so we would be able to know the total mass here. We could add the two together. So then they're blown apart by a little explosive charge in between them. Now, we look at our system as the two pieces together, which would seem to make sense in this case. Then that force is internal, and the momentum before has to equal the momentum after. The initial and final momentums are equal. So afterwards, they're blown apart. Now, I want you to consider what's going to happen here. So I got 2,540 kilograms. And I have 1,240 kilograms. What makes this problem interesting, from a conceptual standpoint, is unlike the Shaquille one and I in the previous video where we're stationary and we could easily say that one of us, quote, moves backwards to the left and one moves forwards to the right, when this is all said and done, my guess is they're both going to still be moving this way. But they did have the same velocity, so when the explosion occurs between them, and a force is applied to this one in this direction, and the identical force is applied here, which one speeds up, which one slows down, compared to the original? Well, if you look at it, this piece here was already moving to the right, the force was to the right, so the acceleration is to the right. So this one is going to speed up. This one here is going to, let's see, the force is to the left, but its original velocity was to the right. Acceleration left, velocity right, that's slowing down. In fact, it could experience, if this force between them was large enough, I suppose it could cause this one to not only slow down, but stop and then speed up in the other direction and actually be moving backwards. But the truth is, in this case, I don't think that's the case. It's just going to slow it down. Now, keep in mind, they were going the same speed. If this one speeds up and this one slows down, what's going to happen to the distance between them? Well, that distance is going to increase, right? I mean, this is going faster than this one. They're going to move away from each other. So if you were standing on this ship when it happened, you would swear that this one was moving backwards. Particularly if you're in space and you have no other frame of reference. But it's not really, it's just going slower than you. So keep that in mind, that can be tricky sometimes. So we're going to find the velocities here afterwards. So for example, and by the way, we don't have to find like the net force or the acceleration or any of that garbage. We can use momentum to do this. After the explosion, the mass of the lower stage times the velocity of the lower stage. In other words, the momentum of the lower stage and the mass of the upper stage and times its velocity when we add those together, that is the final momentum for the system. That means these two should equal the single momentum, right? Mass total, both of them together, times the original velocity, which isn't 0. So it's okay if these two are positive, because they're going to add up to make a positive number. So let's see if we can figure that out. So we start with the idea that since everything's internal, the original momentum and the final momentum are the same. And then we say, all right, in the before situation, before the explosion between them occurred, they were one object. In other words, it was the mass of the lower stage plus the mass of the upper stage, was the total mass, times that original velocity before they were separated. One object. After it, you have two objects. You have mass of the lower stage, velocity of the lower stage. If you like, we put a little f there for final, plus mass of the upper stage times velocity of the upper stage after they separate. So we take this really simple concept and we split it up based on the situation that we have in front of us. And then we start looking at what are we being asked for and what do we have. I wouldn't plug in numbers yet. So if I look at this, I have both masses. I have the velocity before and I have the velocity of the upper stage. So I have the following. I have masses. I have the original velocity. I have the mass of the lower stage. I don't know the velocity of the lower stage after they explode apart, but I do know both of these. So there's only one thing I don't know, and that's right here. So that's what I'm solving for. So I'm going to subtract this from both sides, and I'll get, let's see, we'll just go to green now that we're all together here. So we're going to go ml plus mu times VO minus mass of the upper times velocity of the upper after the separation equals mass of the lower, velocity of the lower after. And then we'll divide both sides by that mass. So mass lower plus mass upper, original velocity minus upper velocity of the upper final, all over the mass of the lower stage. That should give us our answer. Of course, if you'd like, you can plug in, see if you get the appropriate answer, the 3,529. See how close to that you get, but it should work out. Right? Don't cancel this with this. You can't, because there's all kinds of plus signs and minus signs here, so you can't really do that. Just put everything in and take care of it. So there's an example of how to do that kind of problem.